first of all, someone trying to enter, I think. No. Okay, so first of all, I would like to show you a problem that can be interesting. The idea is the following one. Suppose that you have a bacteria. Okay, I have to open from the complex world, my drive, teaching. You should already have this bacteria food on your on the shared directory. Let me check teaching. So you should find it here. Okay, so you have it here. So the idea is the following: you have a source that is emitting with this a certain intensity. I don't know if you see. I may increase the size of the food. Say 1. So okay, so you have a source of food here. Food diffuses and is absorbed when it goes outside our area. And then you have a bacteria here. Maybe we can make the bacteria set size, say 3. Okay, you have a bacteria here. Actually, it is a bug, but it is okay. And the problem for the bacteria is to find where the food is more abundant. But the problem is that differently from classical models in which you compute the gradient of this field, I mean, the particle of food is discrete, and it is of size comparable to that of bacteria. I mean that bacteria, even though it may have sensors on the different part of the body, for him it is quite difficult to compute in which direction more food is arriving, because you consider that you should take count how many food particles are arriving on certain sides of your body, integrate it in time. Be careful, because clearly bacteria can rotate, can move, so it would be a really difficult task for a simple organism, simple say body, a simple living being like bacteria. While it has been supposed that bacteria uses a much simpler strategy. The idea is that it performs random walks with jumps that are larger if it is hungry, and smaller if it is feeding in a good rate. So I try to implement this, then I'll show you the code. But the idea is the following one. Let me go to a certain. So bacteria starts jumping with a size that increases with a certain power when energy goes down. So you see that when energy goes down, it starts jumping to a high amount. So now it is 0 energy. So it is jumping to the largest amount, which I set up to 10, if I remember. So it can start explore. So when it finds abundance of food, the range of jumps becomes much smaller. Now I shall decrease the food intensity. So this is the rate at which food is produced by this patch. Then food is slowly absorbed from the boundary. But you see that the bacteria is able to reach the source of the food by using this very simple strategy. Now I can reduce a lot so clearly at a certain point it starts jumping because it has lost all source of food. So clearly if I decrease this at a certain point, maybe now it has reached the okay, so the energy should go down. Now it is full. Okay, so at a certain point I start wandering, trying to find the source, but when it starts finding the source, it reduces the jumps, and so finally it is able to stay in. So after certain okay, you see now he has found the where food is arriving, and so it occasionally jumps, but it concentrates around the source of the food, and so this it has been supposed to be a good strategy. Clearly, then one can play with, say, the intensity of the source, the consumption of energy at each step, and the factor that influences the correspondence between the size of the jump and the amount of energy. So let's have a check at the code. So I defined the source is represented by, in my case, the source is represented by 1 point only. I don't know, maybe you can connect and share your screen. Maybe I have not checked if it is working on the net, on the web. So let me check. Maybe the problem is that you launched it on the with the web. But I have not, no, because you have the NetLogo and not the web's version. I don't know. If you go with Go, you should see on the source producing with a certain probability these red dots. Maybe you should increase. And so, Lorenzo, I don't know if you want, you can connect and share your interface, because otherwise I cannot really understand. What I did with, I may save this current version. I did the bug greater and also the food larger. Okay, if you set up, just I interrupt the Macron division. So Lorenzo, please show us what happens. So set up. Okay, you press go, and food intensity is try to increase the food intensity. Oh, this is very strange. I don't see. Maybe go to the code and so stop. Try to increase the food in Go. Ask sources in the Go procedure. Set size not 0, but set size 1, because otherwise you don't see anything. Okay, so try now, and probably you had the food, but you were unable to see it. Okay. Okay, so I think we solved the problem. If you put the size of turtles to 0, you don't see anything. So now you can start the bacteria, and you should see bacteria looking for the food. Okay, let me come back to my screen here. So let us check the code. Maybe you can suggest improvement. So the idea is the following. I have first of all, I set up the field. Simply, I make a boundary of white cells. These are only for say having an easy way of making food disappear when it exits our field. The field is quite large. It is about 120 times 60 or 61. And okay, so with this first command, I ask patches which are on the boundary of our world to become white. Then I set one patch in a certain position. The coordinates are such that I choose edge with the origin to the left, so that this is 0, 0. So I can ask patch 10, 0, which is this one, to become red. And then I also defined a global variable, and I assigned this so that I can show you the self command. The self means simply the who is acting, who is executing this command. So this self is patch 0, 0. This is just a way to then address this patch without, say, filtering every time patches with p color equal to red, but essentially this is the same. Then, okay, another late participant. Then I create one bacteria. I assign it some shape, some size. Bacteria, you see, I have used the breed. Remember, breed takes a plural and a singular. So I defined the breed for bacteria and also the breed for food particles. And the bacteria own an energy variable, which is also shown here. Since that I have only one bacteria, I can ask energy of one of bacteria because essentially only one is present. But clearly, I could say, for instance, we can make a version with more bacteria, and maybe here we can show, I don't know, the average energy of bacteria or something like this. Okay, so okay, the color, I put it in say coordinate max -5 and 0. The parentheses are only for easing the increasing the readability of this sentence. And this is just for not starting the bacteria with the food. I can let the food diffuse a bit before starting bacteria. So I define the global bacteria move variable, which is false, and then I use it here to let the bacteria, say, move only when I click the start bacteria. Then say there are not very much. There is only to go, and to go I first of all I emit particles. So I ask sources to emit particles. So if with a certain probability which depends on this variable food intensity, the sources which is on only this red particle, but then we can make a version with more sources. so if random float 1 is less than intensity, it produces one particle of food that takes the shape of a circle. Size, we can maybe come back to point, say 8, and color red. And then I ask all food particles to diffuse. So essentially, it turns their heading in a random direction. It goes with a random amount up to 1. I set 1 in order to be sure that it cannot cross over the boundary here in just one step, because otherwise I get an error. And so if it lands on a patch with color equal to white, it disappears. This makes the boundary absorbing, essentially. I could also have done in a different way. And now maybe we can do a different version. But for the moment, this is what I did. Then, if I click the start bacteria, so if I set the bacteria move to true, then I ask bacteria, and so it eats all particles that are in a given radius. So energy plus count food particles in radius 1, and then it asks all food particles in radius 1 to die. So essentially it eats all particles that are in a certain radius. Then it consumes energy, which is given by this variable here. And clearly, if I bound the energy to 0, I could also bound the energy to a certain higher, so top value. Maybe it cannot eat more than, I don't know. And then the bacteria also turns heading at random and computes this energy to the power minus alpha with a bound to 10, because I suppose that the bacteria cannot jump arbitrarily large. So and so if energy is less than something, it goes up to 10, otherwise it goes to this value. And if can move, so if jumping stays inside the word, it jumps. And so, for instance, we can use this same strategy for food particles. Say, one could, instead of doing this, let me comment, I could let this random float 1 if can move, or if not can move this, then die. So in this way, I should not have need of this white boundary. Let me check. So in this way, no, not something not working. Setup, go. Ask food. Ask Susie if a random float less than food intensity is plotted set shape. Okay. Ask a food particle, set heading, set dist, random. If not, can move and die. Something, say, show I'm dying. Let's see what is going to happen. Go. So they are not dying. I don't understand why it's not. So it's not because they are all dying. If so I'm producing food. Or I'm eating food, but so I'm producing food. So food is produced, and okay, clearly. Otherwise, I have to do forward this clearly. Okay, so this I forgot to move. Okay, so you see that now they should work the same as before. If I put food intensity to 0, they disappear from the boundary. So this is an alternative way of okay, of producing food. And then so I can save it as version 1. Save as bacteria food 1, if you want to check this. And then we may, for instance, try to put more than one source. So more than one source, we can add another slider, maybe here, number sources from 1 to, say, to 10. Let's try with this. In this case, instead of ask this, ask number sources, ask patches number sources. So now I'm scattering sources at random. Set p color red, and then set sources patches with p color equal to red, just to have an easy way of addressing them. So let me ask ask n of number sources patches. Okay, so now I have a certain number of sources, and when they go, they emit this. Maybe they emit a small number or small rate of food. And so now bacteria, but maybe we have to decrease a lot the food intensity in order to see if bacteria can switch from one source to another. Okay. I don't know why he's not eating. Let me avoid the tracking, the pen down of the bacteria. Otherwise, we don't see anything. So they emit. Okay, start bacteria. I don't understand why. Probably because there are too few amount of food. Okay, now he's able to find some food. Maybe we can now reduce the food intensity so that at a certain point it should switch to other sources of food. Okay, so yeah, these are only experiments. So maybe we could reduce also the food diffusion. So instead of say instead of putting simply one, we can random float food diffusion. So now I should be able to have very small food diffusion, see, and so maybe now bacteria, you see now is feeding on this source, but when it has exhausted this source, is passing to another one. You see now energy is decreasing, or okay, maybe we can reduce the food intensity. So when it has finished the, so now you see that this strategy is somehow working when it finish the food, they start jumping at random until he finds another source of food. So it could be a reasonable strategy for finding food sources. So maybe I can save this as a version of, say, multi-food, bacteria multi-food, say. And clearly now we can also add say also a number of bacteria, slider number bacteria, or maybe we could allow bacteria to reproduce. Okay, for the moment, say from 1 to 10, number sources from 1 to, okay. And so create bacteria number bacteria, and now we can say random X core, random Y core. So now number bacteria. Okay, so now we have a certain number of foods, a certain number of maybe now it is too little, so we have to increase. And you see that most of bacteria, some of them is always wondering, because we have a very little source food with respect to the number of bacteria. But if the number of food sources is good enough, you see bacteria are feeding on food sources, and from time to time they start wandering to look for another source of food, and so it is a reasonable self-organization method to find food sources. So are you convinced of this example? Let me save as multibacteria multifood. Questions? Okay, if everything is clear, I can show you Okay, this was just an exercise, but this night I was thinking to this old model. I've read some article about this Levy walk of bacteria, so I wanted to check if it is if it was true. Let me check another aspect. For instance, let me take some model. Okay, for instance, we can. I would like to explore the this behavior space, which is a way of running experiments with varying some parameter and monitoring other parameters. So let us try with some very simple, say, model from the library. So model library, we can take, I don't know, game of life. Okay, we can, let us set up the game of life. So from ourselves. So new. The game of life is a very simple model in which I have a certain number of cells. Say, let me consider, say, initial density from 0 to 1. Okay, and to set up, I ask patches if random float 1 less than initial density, set p color white. So this is very simple. Okay, so maybe set up. Okay. Clear initial density should be something like, okay, maybe I have to clear all, set up. Okay, so this is our field. Say, suppose that white means alive and black means dead. The rule from the go button, for the moment without forever, to go, I ask each cell to compute the number of cells in the 8 neighbors that are alive. So patches on save alive neighbors. So I first ask patches set alive neighbors count so neighbors are the number for let me check in the dictionary. I want to show you NetLogo dictionary. So neighbors is the set of 8 surrounding pages. So neighbors with p color equal to white is the number of neighbors which are white. Count is a number, and so each patch is, so if I go step, I now inspect these patches, and it has one alive. So these patches here has just one alive neighbors, while this patch here, for instance, it has 2 alive neighbors. Okay, and now the evolution rule is the following. if color equal white and alive neighbors equal, let me write for the moment just to some in this way. This is not correct, but assume that this means that it is 2 and 3 and color is equal to white. So it means if it is alive and is surrounded by 2 or 3 alive, it remains alive, and otherwise color equal to black and alive neighbors equal to 3. So the rule is if it is dead, it becomes white or becomes alive if it is surrounded by 3 neighbors. And if it is alive, it stays alive if surrounded by 2 or 3 alive neighbors. Otherwise, it becomes black. So we can say use, for instance, if else value. So now I have to put something here for the moment and just write like this. So if this is true, it is white, otherwise it is black. And so you see that when alive neighbors is 3, either if it is white or black, it stays alive. So I can write alive neighbors equal to 3, or color equal to white and alive neighbors equal to 2. So I can simplify the expression in this way. So essentially it says if color, quindi set color if else value, so if alive neighbors equal to 3 or color equal to white and alive neighbors equal to 2, it is white, otherwise it is black. So essentially if I p color, not color, p color, okay. So let's go for a moment in order to reduce the amount. So you see, okay, this block is stable because each white patch in this block has 3 alive neighbors, and so it stays white, while the black patches around this block has alive neighbors equal to 2, but they are black, so they cannot become alive. You see, for instance, after some point, you can check that this is also true. There should be also some oscillating patterns. Let me go on. Okay, so for instance, this is an oscillating pattern because the center one is surrounded by 2 white patches, so it stays white. This black here is surrounded by 3, it was black, but it's surrounded by 3 white neighbors, so it becomes white. And the 2 cells or the 2 patches on the boundary are surrounded by just 1 white cell, so they become black, and so they oscillate. And the nice thing of this game of life is that it has a very, so maybe we can increase say 40 by 40 in order to appreciate the complex behavior of this model. too much. Okay. So you see why it is called life, because it has a behavior that resembles that of living, say, set of, say, game bacteria. You may also notice that there are interesting patterns that propagates, like this one. You see this one is advancing. They are called the gliders. And so they can, say, propagate life from one side to another when they meet some standing pattern. They are called, these not moving patterns are called still alive. They can reproduce. And what is interesting is that it has a very long transient. So maybe we can measure reset ticks and then tick, just to have an idea of how many ticks it takes, reset ticks, to arrive to some stable pattern, the order of some, say, 1,000 or 2,000 time steps should be sufficient. Okay, so now we see that, for instance, if we start with very small initial density, it goes extinct. If we start with a very large initial density, it goes extinct. And in the middle, it should be able, maybe making the lattice larger, to arrive, say, maybe we can compute some, say, count patches with p color equal white divided by count patches. Patches, maybe we just need 3. Display name density. Okay, so the idea, okay, you see it arrives to a certain density, about 0.03. Maybe we can change this. It organizes, and after some, say, large transient, it arrives to a certain density. Okay, say we need some 5,000 time steps. Now the idea is we would like to perform a certain number of experiments by changing the initial density, measuring the density, maybe doing it for several times, but automatically. And so let us save this as well. Maybe I have already life here, so this could be a simple life model. Okay, so now let's try to use this behavior space to explore this the behavior of this system. So I may name this experiment simple life. So here I vary the variable. Maybe we can go to the help in order to here behavior space. So you have here all the help, And so, for instance, if you want to vary, as we want to do, some variable from, say, 100 to 1000 step 50 units, you have to put in parentheses. So we want to start this from 0. For the moment, 0.05. In step 0.05 up to 1, from 0, say, from up to 1. So this is our scan of initial density. We can ask how many repetitions. For the moment, we can do this just once, and then we can define what we want. The measure that we want to perform, behavior space. I have to restart. The measure is this one. Here we said 0.0551. We want to measure this density. Maybe we could have defined a reporter to this. Run metrics every step. No, I don't want to run metrics every step, but only at the end. New experiment, simple life. I have to save this simple life. 0.051. Let me okay, otherwise I want to check this. No, I don't know where it has went. Okay, these things here. Copy, cancel here. Okay. I don't want to run metrics every step, but only at the end. I hope it is going to. So time limit, say 4000. Okay. So let's see what happens. It produces a spreadsheet. Let's see what is happening here. So, okay, it has already performed this experiment. Let's see what produced. I don't remember where I put. Okay, this should be the experiment. It produces a comma separated value. Okay, it's still working. Don't convert. So finally it should have ended. And so you see, here is the number of experiments. Clearly, the interesting point is that they are performed in random order because it tries to exploit all the processors that are in your computer. So in this case, we have, maybe I can show the system load. No, maybe with another interface. So here you see the occupation of processor in these machines. You see I have 10 processors, which are, except these two here, essentially idle. But if I run my experiment again, you see that it runs 7 experiments in parallel, and so now you see that all processors here becomes 1, 2, 3, 4, 5, 6, 7, at least 7 of them, plus maybe 1 for controlling, is becomes busy. So it is running the experiments. You see here what is going on. At the end, it produces these two spreadsheets, one with say an horizontal view and one with a vertical view. Essentially they are the same. And here you have your the result, so the density. And so for instance we can now plot, if I remember how to use Excel, insert maybe from here, insert a chart, scatter. Okay, so not really a nice plot, but you see that because also the size was not so big, you see that for small values we got 0, for large value we got 0, and for the intermediate value, except some cases here, we got say almost a constant value. Maybe we can increase the size, say 100 by 100. Let me put this one. So now we have a larger sample. Maybe we have to wait for a larger time. Say, let me edit this. So maybe with a 10,000 time steps. Okay, and so we may run. Okay, maybe we have to wait now a larger amount of time because it has to run the experiment with larger lattice for a longer time. So this is still run number 4. Probably the first 3 ended because of a small amount of time. And okay, we can also have a look at what is going on. Clearly, this slows down the simulation. Okay, maybe we have to wait some more time. I don't. Okay, so maybe we can leave it run for a while, and while we wait, we can say, you see, it is working full time. So we can start to say another NetLogo issue. While this is still running, and so this can be. Now clearly I have only one free processor, so also this machine becomes quite slow. And the last thing that I would like to show you is the HubNet. HubNet is also described in your manual. Hubnet is a way of running simultaneous simulations from different computers, different interfaces. It only works um, with the desktop application. There is a project of allowing it also to run from the web application, but there the the problem is how to communicate, because clearly you have to run it on the server. But there is also a project on this. So let us open for the moment a standard model library, the simple Hubnet example. I don't remember this, the Hubnet activities code example. I don't remember if it is, probably it is this one. Okay. Okay, so first trial. Okay, so when you run a Hubnet example, a Hubnet code, now your NetLogo interface is the server, and this is the Hubnet server, and you have to use another application, which is the Hubnet client, this one, in order to connect to the server. So assume that all this that I put here is on a computer, and this is our running experiment that I remove in order not to have in the view. I remove also this one. Okay. Now, this is a client, so Franco, for instance. The server is this one that I see here. Here I see all servers that are present on my network. So here in the Hubnet control center, you see that Franco joined from a certain computer. So in this way, there is only one actor here. So remember, this is on my computer and this is on the server. So for instance, I can move. Now we can see the code, and I see what happens in my view, and also the master who is running this server can watch what is going here. But I can restart. Now I want to launch another application, another copy, as if I were on different machine. I have to launch it from the command line because the Macintosh operating system, as a Windows does not want to have more than one application with the same name, but I can run it from the command line. Okay, maybe here I am, I don't know, Julia. I connected to the same server. Okay, so I also enter as Franco. So now assume that this is on one computer, Franco's computer, and this is on Julia's computer. Here you see that I have two clients connected. I can see them. So one moves here, other moves here, and then clearly I can do some some action according to say where they are and so on. So let's have a look at the code. The code is a bit different because now the interfaces only reacts to messages sent from the server and responds with messages. So this is running on the server. Okay, so you see that we are students and we own user ID and step size, okay, which is this one. But actually, this is not the NetLogo interface. I cannot edit here from here. I have to edit, I shall show you from this master issue. Then there are two procedures. Startup. Actually, this happens in all NetLogo. We only use the setup. But if you want, you can use also startup, which is run when you open NetLogo, when you load this code. So it immediately runs a startup. And then when you click setup, you run this, which is a normal procedure. So this is a special procedure that runs only once at the beginning of the model, or clearly when you type startup or you use the button startup. So this essentially resets a hubnet in the sense that when I run a startup, I disconnect all clients. So I have, for instance, to reload. Then to set up now, I don't use a clear all because the setup maybe can be called by the master when he or she wants to say bring all students to the initial points and so on. So I'm not destroying patches. I'm only clearing patches, clearing driving, and clearing the output, but not clearing turtles. Because I assume that turtles are created when, I shall show you, when clients connects. Okay, so you see, the go procedure, you listen clients, and you do nothing. Listen clients, clearly it is the go procedure is here. So essentially you have to check if some of the clients has sent a message. So is there some message waiting? If there is a message, you fetch the message. And if it is a special message, it is the message received when I log in. I call create a new student here, create a new student. If exit, it is the message that I send when I exit. For instance, I close this. I remove the students. So for instance, here, let me move a bit. So if I close here, you see that I remove the client here, remove students. I remove this. And if I enter again, I received this Hubnet enter message. Maybe we can say show someone wants to enter. And so if I disconnect, okay, if now you enter, I should have seen something here. I don't know why. in principle, it should show someone wants to enter here. I don't know why. Okay. And otherwise, it asks, so it has two turtles called the students. Each turtle has a given user ID, which is just the string of the name. So it can ask a student with the user ID equal to Hubnet message source. So and then since I have assigned here user ID Hubnet message source, which is clearly the name that I have chosen here. So I can just ask to this turtle to execute command, which is the body of the message that I have received. So essentially, when here I click up, this interface is sending a message to the server saying, oh, I am Franco, and the message that I send is, say, move up. So here it is, execute command. So I can send a message, step size, up, down, left, and right. So you see, if command is a step size, it simply changes the variable step size. If command is up, it execute move, which is this procedure, to 0. Down 180, right 90, and left 270. And this simply set the heading to this value, forward the step size, and then I have to, so this, if I comment this, I move, something is not really working. Let me start again. Okay, so let's try again, enter. Okay, now set up, go. Okay, now I still sending message to clients. Okay, I'm not sending this position, only updating the view. Okay, so this is for sending, should be, let me see, send info to clients. Send info here it is. Okay, so as I said, this send info to clients, it only is needed to change this, no? It's Hubnet send, user ID, location, etc., etc. Okay, so now you see that here it also, I have to restart everything in order to have this executed again. Now you see someone wants to enter, and if to reactivate the send info to clients, I have to restart probably. Start up. If I now connect again, and okay, set up, go. Now when I move, I see this location changing. So I said that this is not the same as this. You have to use this Hubnet client editor, where you can, say, place things where you want, and then you save. When you, this is now they're slightly different. You have a tag for each of these, and simply it sends this message. So when you click this button, it sends the message left, and which is processed here. Okay, and so for instance, if I now save this, I restart. When I enter, you see I have now a different interface, a different view, because I edited this HubNet client editor. Okay, so what can I do with this? I would like to show you an example that I already loaded in your shared directory, but first let me check if this has not finished yet the experiment that we run. So okay, let me start with so first of all I start with I leave this HubNet here just to be reused, and then I discard this, and I start another item of NetLogo. This is HubNet client. No, I don't want HubNet client. I want in NetLogo. Okay, let me launch, because I still have the old one running. NetLogo. Okay. So I would like to set up a very simple game, which is a Formula 1 run. Then I'll share also this. So you should already have it on your shared folder, and should be named racing here. So the idea is that I have a circuit, and when I start, I can use speed up. Okay, I can use the keys in order to increase speed, decrease speed, brake. And the idea, now I have to brake, otherwise out of circuit. So if I start, let me go slower this time. Okay, so the idea, clearly, this is a simple training experiment, so that maybe I could add Hall of Fame and try to fulfill the circuit in a smaller time or something like this. So first of all, let's check how this works. It is not very difficult. As usual in NetLogo, it is just 2 pages. So essentially, I have this factor, maybe it can be less than this, which is that just a way of controlling how the speed increases or decreases when I type A or S. So it may be, say, could be also a slider here. It is just, you see, a way of say, having more or less control on the speed. So essentially, it could be a difficulty factor, this one. Okay, so first of all, you see that I can input this scenario onto the colors of patches by inputting an image. So this is interesting because you can use some, for instance, a PowerPoint or some other image editor in order to change this. Let me see. I should have also some other. Let me see. Okay, for instance, I have here other circuit. Maybe I have Imola and Monza that I can copy on your shared directory. Oops. Introduction. Oh, this is last year. Introduction NetLogo 2000 here. So Imola and Monza. Let me see. Okay. Okay, so maybe we can set up. Okay, now I should be able to input the circuit, but then I have to change this algorithm to draw the starting line. So maybe let me come back to racing. But you see that you can essentially do. I have not adapted the code in order to have a flexible. So maybe I should keep this starting line constant and change the shape of the circuit. Okay, and so in any case, this is for showing that you can input the background of your patches. Then this is the line, the end line, and so these are 2 points that establish the length of this. I shall show you that I used some geometrical computation in order to check when this card is crossing this line. But in any case, I use a patch to draw this turtle, to draw this green line. So I create a turtle, set color green, set pen size. It goes from one of these 2 points and draws a line to the other points. Then just wait a minute, because I have a phone as always. I don't know where it is. Okay, but okay, and okay, then I create the car. Clearly, I use the shapes editor to draw the shape of the car. Here it is. So you don't see, but there are black wheels, and the body is this one. And okay, so this is all for the setup. Then clearly I place my car in the right position. Then this button simply calls some procedures. So to speed up, I have only one turtle, so I can address simply set v plus some delta v, which is this one. It is another difficulty factor if you want. For factor, to brake, I decrease the velocity. To turn left, I turn the heading some amount, 5 degrees. Turn right plus 5 degrees. And to go, here is all the body. So this is just for stopping the procedure when clearly when it arrives at the end or crashes on outside. I don't know why, but in NetLogo stops only works if it is at the end of this loop. So I use a flag to check if I should stop, and then I stop. So essentially, this is for step A. Step B is to check if it crossed the green line. So for the moment, I do not consider this. It simply goes forward a certain amount. If it has landed on some black patches, user message, you are out of the circuit, set stop through. User message clearly makes a user message to appear and stops. Then the other, so I, in order to see if I cross this line, I set the first point, the last point of my segment of this in this amount of time, and then I check if this segment crosses, intersects the segment of the arrival line. Then I have here some geometrical computation. In case there is an intersection, you arrived, set stop through. So, and in order to check for the intersection, the idea is that the two segments intersect if so it is a bit I should draw something maybe on some paper. Notability here, say here. So a segment from point A to B intersect a segment from point say C to D if the triangle, this triangle and this triangle has a different orientation. I mean, if you percord this triangle, for instance, this is a negative orientation because it is clockwise, while you have to keep the same orientation on this. While this one is counterclockwise, so it has a positive orientation. And the orientation, this and this are both opposite sign. Because you see that if you take a segment and another segment, say A, B, C, D. If they do not intersect, this triangle and this triangle have the same orientation. So you have the intersection only if all triangles have, for a given segment, for the two segments, have different orientation. And so in order to compute the orientation, you have to perform the cross product. So this is the cross product of two, and I just check if the cross product is negative or positive. So I moved this on the opposite side, but essentially you can write this, which is the cross product less than 0 is the same. And so I come back to this. And then, so this is just the orientation of a triangle. So I have orientation ABC different from orientation ABD, and the orientation CDA different from orientation CDB. So if this is true, these two segments are crossing. This is not exactly the whole procedure, because I should also check if they are collinear, so if they overlap. But this does not happen here, because it is extremely difficult for you to go in overlapping on this line, and so I have not put this. Okay, so this is the simple racing. And now I want to convert this into a two-player game. So I open the multi-racing. Okay, so I don't know, Imola. Okay, so now this is the server. Now we can check the code. For the moment, do not look at this. Then I take my two, say here, clients. So you see that Franco and Giulia joined this. I set up, and when I go, Franco and Giulia are here, so each of them can, say, speed up and so clearly for me it is difficult, because I have to drive two cars at the same time. So let me go not so fast, otherwise. Okay, so for instance, here Giulia already had exited the circuit, so let me start. Okay, go. So let me start again. Turn left. Clearly, you have to, if you really want to okay. If you really want to play this without, say, being in the same room as the server, you have to use messages to say, okay, ready, go, and so on. So I have to, Giulia is, okay, it is difficult to drive two cars at the same time and so to speak. But essentially, this is what I wanted to show. We can have a look at the code now. The code is very simple and very similar to the other one, but clearly we have to consider some more cases. So essentially, this is copied from the sample example that we have seen before. So this is the procedure that is called at the beginning, when you load everything. So essentially, you reset the hubnet, you clear all, you import the map of the racing. You you define something, and that's all, not very much. To set up, you clear things, for essentially you clear the output. Then this is for drawing this line. Probably it could have been done also here. No, but here I have clear output, so I have to redraw the green line. Then remember that here I'm not creating cars, because when I press set up, people has already connected, and the cars are created when they connect. I shall show you. And so cars are already created when I press set up. So I just put the cars here on the line using their number, car 0 and car 1. And okay, I reset something and so on. And to go, okay, let me, okay, to go is, no, okay, before I have to, here, create new car is when they connect. So when they connect, they send a message, abnet end message. They just, when they connect, they just simply send the message. For the moment, it is not processed. It says it is processed when I click go. And indeed, you see that if I restart, okay, I reconnect and I reconnect. You see this because it is the interface, but you don't see the car unless I press go. When I press go, then it starts listen clients. So it says that it has an hubnet message, enter message, so it creates a new car for Franco and for Julia here, which is not very complex. And okay, so listen clients. Then here is the evolution, which is processed on the server. So I ask car, if not stop, because clearly stop can happen because one of them has crashed or has arrived at the end. So the other one could say should stop, otherwise maybe both could crash. And I do not know who has crashed before and so on. So they this is the message that will be shown here. For the moment, it's just a variable. Set message this, go on, or okay, this is the user ID. So Franco, maybe virgola, comma, Franco, go on. Oh, go on. Okay, then these are the same procedure as before. Forward, if color black message now it is not this but out of circuit. No, user message is another variable that is sent to the message. Okay, user message. Sorry, user message was what is shown here on the server. Just to inform the controller that user ID is out of circuit, and then I stop. This is the collision from two cars. If R is half of the size of the car, so if there is another car in this radius, I set the message collision. Here it happens driver collided, and so on. So let's check this, for instance. So go, I speed up Franco for something, and then I stop. speed equal to 0. Then I speed up Julia, and then I send Julia on Franco here. At a certain point, okay, driver Julia collider, this appears on the master, and here we have a collision. Okay. Someone wants to participate. It is a bit late, but let me allow. Okay, and so then after having updated this, I have to send things to clients. So essentially, when I click on this, I'm sending a message to the server, and which is processed here. Then after having updated everything, I send info to clients here. I should, well, this could be moved also outside these ASCIIs. Send info to clients is this one. No, I have to send, I send it to user ID, the message has user ID speed. So this is used to update this and this here. So I have to send for each client. While execute command incoming from a client is here. It is, so this is just for debugging. So it is what is shown here. So you see, I show the command received, so speed up or break, and then 3 dots, and then who sent message. So maybe I could have wrote this in the opposite order, say, here. Okay, so maybe this is more correct. Let me see. Start up. Okay. Oops. Enter. Okay. Enter. Setup. Go. And okay, you see the message is Franco turn right, Julia turn right, Julia speed up, and so on. And okay, and then we have to process the messages essentially with if, or if else. So this is the idea. Not quite could be useful. Okay, so I can save this so that you can play with this. Clearly, in order to use this, you have to be on the same network. So if you want really to play this, it is quite easy if you are in the same classroom, so that you connect to the same Wi-Fi, and so you can find the servers. Otherwise, you have to to play a bit with the tunnels, so which are not a topic to be treated in this course. So just to end up, we can, let me say, check if the experiment, you remember, we were waiting for this experiment, the behavior space. So I hope this simple life has finished working, so that I can also save this. And I should have here the the two spreadsheet produced by the experiment here. And now I hope that the plot is nicer than before. So insert the chart scatter. Okay. So now you see that maybe I don't remember how to use this. Solid line. No, maybe all of them. Solid line. Okay. Okay, I have to sort probably data. Some sort. No. Maybe I can just sort all of this. Sort. Where is? Here it is. Sort according to initial density. Sort on values. Column initial density. Okay. And now you see that the plot looks nicer. And so this is the idea that NetLogo is quite a slow language, but it can be used, for instance, using this behavior space in order to automatize some of the simulations. I think that for today and for all the courses, this is enough. Clearly, I would like to hear from you. If you use NetLogo for something, let me know. And don't forget to sign up to the form for the lessons that you attended, both online or recorded, so that I can, in a week or two, I can send the list of attendees to the administration to be inserted in your curricula. Okay, I think that is enough, and see you maybe in the next course, which is the history of computers.
When will be the next course, Professor?
Next course will start on the 7th of May from Babbage to ChatGPT. It is offered from the Department of Computer Information, but it is online as this one, so you can attend. If you are interested, I can send. I think you can find the information in the same place as the other. So teaching, I would put it there. So for the moment, probably they are not here, but here from Babbage to ChatGPT, and there will be a form also to sign up here as before. And I'll put the information and the recording here.
Thank you, Professor.
Okay. So, bye-bye.
Thank you, Professor. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye.